OK. So maybe I will very quickly remind you of what I did last week, and it will be the occasion for asking questions if you've got any. So what did we do last week? What we wanted to do was we wanted to enumerate maps. And for that, we did build some generating series, which generate the number of maps of some given topology. And we started by looking at the case of genus 0 map with one boundary or one map face of arbitrary length. And we found out that we can get it by just solving a quadratic equation, which we can find explicitly in terms of the weights that we put on the maps we want to enumerate. And actually, something we can do is associate to that a Riemann surface, which is defined as the pair xy. Oh, sorry. In C, I mean in the Riemann sphere, such that E of xy equals 0. Mainly, this is what we did last week. So associate to a problem of enumeration map a surface such that the algebraic equation which defines it gives me my W01. And one way to think about that is to say, in this case, I'm very lucky because my surface is a genus 0 surface, so I've got a rational parametrization. I can find a good parametrization of it. Write solution to this equation as function x and y which are rational in a parameter z. And in this way, we get that W01 as a nice expression in terms of z. Now, what we will do today is to, and yeah, I don't know if we will have time to make it today, but at least tomorrow, is to apply the same kind of program for genus G, generating series of genus G maps with n boundaries. So what we did last week in order to get this equation was the following thing. We derived some combinatorial equation, which are satisfied by the coefficient of this W01 of x, Tutte equation. And we did translate that into an algebraic equation. Now, what we will do now is to generalize that for surface for maps of genus G with n boundaries. So yeah. So what we call a map here, for people who are not doing combinatorics, it's a bit misleading. It's not a map from something to something else. So I spent some time explaining what it is, but a map basically is a graph embedded in a genus G surface. And n here stands for the fact that my map, which is, or you can think of it as a discretization of a genus G surface, it has n marked faces. If I mark n faces, I can think of it as removing them from my surface on which I've drawn my graph, and then I can think of them as boundaries. Okay? Yep. Any other question? No? OK, so now what I will do now is to generalize the procedure I used in order to get this equation, which was Tutte's equation, and which in this more general case were found by Walsh and Lehmann. And you just proceed exactly in the same way. You consider genus G map with n boundaries. And arbitrarily, you choose the first boundary. And I will draw it outside. So it means that I've got my boundary, which I put outside. Remember that there is one marked edge here. Inside, I can have many things. So I will not for everything here. But now what is different is that I've got the genus G map. So I draw it on the blackboard, and in order to remember that I've got the genus G map, I draw G handles inside my surface, inside my map. So here you can have some more discretization. And in addition, I've got n boundaries. So I did draw one here, but I've got n minus one more, which are marked faces. Each of them carrying a marked edge. So these are the type of object I have. Now I do exactly as I did in the previous case where G was equal to 0 and n equal 1. I'm sitting outside here on my marked face, the first one. And I'm wondering what happened when I cross my marked edge. So I start from an element of mg L1 plus 1 L2 to Ln, where L1 plus 1 is the length of this boundary. L2 to Ln are the lengths of the respective boundaries of L2 to N. And now what can happen when I cross my marked edge? On the other side, the first thing which might happen is that I've got eigen which is not a marked face, which means that if I remove that, I end up with something very similar. No, yeah, it could be. I will consider this case. So I'm just enumerating all possible cases. So the first case is when I cross it, it's not a marked face. So yeah, in the preceding case when n was equal to 1, I didn't have the possibility that it was a marked face. So I start from this one. I still have the same thing. And here, and I've got my other marked faces. Now, my marked face is still outside, and I choose to put my marked edge here. What do I end up with? It's exactly as we did in the preceding case. I still have a genus G map. The number of boundaries is still equal to n. But now the first boundary, which had length L1, now has length L1 plus I minus 1. And the other one still have the same length. So remember that when I remove one edge, this edge has two sides, one belonging to the marked face and the other one to the inner face. And so what I get is that before I had L1 plus 1, remove this edge, I've got L1 plus I minus 1. So I start from an element of this set, and I get an element of this set. So that's the first possibility, but now I've got many more. So here now I don't draw what is inside, I just draw it in this way. No, second case, it might be a marked face. So marked face, and I want it to, yeah. Where? In this case?
Yes. It might be that you can have multiple markings on a single face.
No. There is only one marking which is such that your edge is oriented in a way that on your right side, you've got your marked face.
The same face could be marked multiple.
No, just once.
Just once?
Yeah. And that, I mean, when I say that it's marked once only, it means that I could have something like that. So it's a different face. And this is the only possibility, and it just gives me exactly the same kind of contribution. Now I'm here, I've got my marked edge. So now what can happen is that it's a marked face when I cross it. Now this marked face might be a different, let's assume first that it's a different face compared to the one I had to start with. And I've got a marking here, such that my marked face sits on the right side. Then I start from this, L1 plus 1, L2, Ln. Let's say that here I've got the chase, the marked face. Then what I get when I remove it, it's exactly the same procedure as before. Yep. Here I still have my small squares, my other marked faces. No, this face was marked already, so I don't have to choose any marking. If it happens that this marking is there as well, then I mark exactly as in the previous case, the first one to the left. Now, what I get is still an element of mg. Now, here, when I do that, you see that I go from n marked faces to n minus 1 marked faces. The first boundary now has length L1 plus, if here I've got the j marked face, plus Lj minus 1. It's like having a Lj gone. And here I've got L2. I don't have Lj anymore. 2Ln. So I've got still a genus G map with n minus 1 boundaries now. Yep. Now, let's keep on looking at what happened and can happen. So first case, on the other side is an unmarked face. Second case, on the other side is a marked face, which is different from the first one. Now you just have the cases where it's the same marked face. So you remember this kind of drawing. So still an element of mg L1 plus 1 L2 to Ln. Now, you wonder what happens if I remove that. First, you see that you've got your other marked faces can be on both sides. You have all possible cases. But remember, I've got a genus G face, so I've got these handles. First, look at the case where these two components are such that you don't have any handle going from this side to this side. Such that if I remove this edge, I disconnect my map into two parts. Then what I get is just an element of this type, where now I use the same procedure as before for marking my new edges. I've got a disconnected map of this type. Can you read it here? Yeah? OK. Where now I've got two disconnected components. The first one belongs to some set M, G1. So depending on the number of handles I've got on each side, let's say G1 is the number of handles that I've got here, belongs to MG1. And what do I have? I've got some, first, a boundary which comes from the original first boundary. Let's say it has length J. And it's got many other boundaries. So I will use a notation, which is the following one. If A is a set, then LA denotes the set of elements Li, I being in A. So what I will do is that I consider a partition of 2n into two subsets. So I take A, B is equal to the set 2 to n. Take an arbitrary one. And so what I did is just disconnect my map into two parts, one of genus G1 with cardinal of A plus 1 boundary, and another one of genus G2 with cardinal of B plus 1 boundaries. So you've got LB corresponding to all the boundaries which were already there. And you've got a new one, which is now of length L1 minus J minus 1. Yeah. So I started from L1 plus 1. Yeah. OK? Sorry? You can. So for arbitrary G, no, for arbitrary G, L1 can be, so if you take G equals 0 and N equals 1, it could be equal to 0. But indeed, I mean, so the whole question is whether I would allow it. Let's say I allow J equals 0, but then this set is empty most of the time. So yeah, here I didn't say which J, value of J I allow. And this is what I will do just after. Now I look at the same exact contribution, which is when I cross it, I go to the same map face. But now if I've got a handle going from one side to the other one. So I still have my map faces, which are my other boundaries. And now I assume that I've got a handle going from there to there. Yeah, I know that I'm not very good at drawing. I hope that everybody understands what I mean here. So I start from an element of mg, L1 plus 1, L2 to Ln. What do I get? Exactly the same picture as before. Where? Yeah, I might have. Oh, no, it's just it's shorter. I mean, you just have the same number of sides, right? Yeah. Just a topological object. OK, which is of this type, and now I mark the faces as before. Now, what does it belong to? Sorry? Yeah. Yeah, you could. So the question I ask is the following one. Does it, what? It is, it's a bad drawing, I agree.
I mean,
but I cannot draw.
Is not connected.
No, you've got one more boundary component now. That's the thing. How can I draw that? What would be the easiest one? So here, what happened here? You started from one boundary component and you add one more. So your original boundary component has been separated into two parts. Okay? That's exactly the same thing here. The point is that since I'm drawing on the blackboard, it's very hard to write down homogeneous cases. So, sorry? Yeah. No. You've got more boundary components here. You've got one more here.
But those two red things are connected. The whole exterior of your two pentacles.
No, they are completely disconnected. You can think of them as disconnected objects. Because what I don't want is a map which is of the. So if you want to think of it in this way, what would I have? Would I have a map such that the face is this whole blackboard, So it's not simply connected anymore. I don't allow that, so I just cut it here. Yeah.
Same as you did.
In the previous, yeah, exactly. The issue is that if you want to do that for higher genus, and this case happens only when you are in higher genus cases, you've got to draw it in some other surface. And you do exactly the same thing. In the annulus that you did create in this way, if you want, in this higher genus case, let's say that you will create, so you start from this, you remove your edge, you create an annulus, then you pinch it into two parts. Is it clear? So I've got the torus, I've got my marked face here, with my marked edge in the middle. If I remove it, I've got an annulus, and then I just cut it into two parts. So yeah, exactly the same procedure I did before. So now, what do I get? I had a genus G surface here. But when I remove that, actually I end up with something which is of genus G minus 1. Maybe I should have left my picture here. So what I did is pinching this part. So I start from genus 1. And it means that I end up with something like that. A genus 0 surface. So I lose one genus here, one handle. And now the boundaries, I've got as much as I did here, meaning that I've got n minus 1 plus 2. So I've got n plus 1 boundaries now instead of n. And their respective length is j, L1 minus j minus 1, L2 to Ln. Now, by all these drawings, I did exhaust all possible cases. So this is just a natural generalization of the case which was g equals 0 or n equal 1. Now, what did we do after that? We said that it was a bijective procedure, so it allows us to count element of this original set in terms of element of the different sets I get by this decomposition procedure. Here, it's exactly the same, except that in some cases you can have some redundancy, which is that in this case, because of the marking of the inner edge, if I look at this element, before I could go back because I had a bijection. Here it's not the case anymore because I could close it either where I did here, but to get an element of this set, I could close it here as well. And this corresponds to all possible respective position of this marked edge compared to this one. So starting, OK. If I start from an element of this set, and I want to recover one element there, I need to tell you how I do that. Before, it was pretty simple. We were in this case, which is the following one. The inner eigen didn't have any marked edge. So for going there, I did mark the first one to the left compared to this one. Now, it means that if I got an element of this type, I know where I need to close in order to go back here. I need to start here, and I need to close in this direction such that I've got an eigen inside. So it fixes exactly the endpoint.
Yeah, in this case, over there.
In this case, yeah. In this case, it's not as clear anymore. If I start from there, I could close from here, which is what I did come from, but I could close from there. And also, and you can have a special case. So you've got actually LJ cases which can happen. And this will give you a combinatorial factor. So it's not a bijection, but it's not far from it. And we can enumerate all the cases. So in order to get a bijection, you would have to remember exactly where the starting point is. So now what I want is to enumerate genus G maps with n boundaries. So I want to have Tg L1 plus 1, L2 to Ln. And I decompose it in all these possible cases. First case, I've got an element of this type. So I've got a contribution from Tg L1 plus I minus 1, L2 to Ln. T is the weighted sum over element of this set. So it's a sum over. Sorry? No, W is after that. I will go back. I will go to there after that. W has some x1 to xn. Yeah. So these are generating series for the T's. So I've got this weight, but remember that to I-gon, I've got to weight Ti, which is associated. So in order to recover the right weight here, I've got to multiply by Ti. And I've got to sum over all possible values of I, which range from 3 to D. So it gives me all the contribution coming from this kind of configuration. Now this kind of configuration gives me a sum over all possible faces which I've got here. So it's a sum from J equals 2 to N. I've got some T, G, L1 plus Lj minus 1, L2. I don't have the Lj, Ln. But because of what I told you before, that there is this issue of knowing where I start from, I've got a factor here, which is Lj, which is the number of ways I could close an element of this type in order to get an element contributing to this one. And now, now I've got these two last contributions. Is there something missing? Also? So capital T is the weighted sum over genus G, genus G maps with n boundaries of respective lengths L1 plus 1 up to Ln. When I say weighted sum, I make a sum over such maps, where whenever I've got an unmarked face which is k-valent, I give it a weight small tk. And so if I want to recover the right weight here, since I remove an I-gon unmarked face, I've got to multiply by the weight it had before, so this Ti. Here I just remove. No, this is a marked face which I removed here, so it didn't have such a weight. So the TJs, they just came from unmarked faces. Marked faces will be weighted by x's, powers of x. And this will come in the second step. OK, so these are the two first cases. Now, this one, I'm considering all possible partition of the set 2 to n. And the composition of G into G1 and G2. So all possible ways of distributing other boundary components and other handles. And I've got just a product of this type, Tg1. Tg1 J LA, Tg2 L1 minus J minus 1 LB. And I've got to sum over J equals 0 to L1. Is it L1 plus 1?
There's two pages missing from the...
So yeah, sorry, right. L1 minus 1. Where in most of the cases, this will be vanishing for J equals 0, except in the case where G1 equals 0 and LA is equal to 1. And the cardinal of A is equal to 0. Sorry. So A is empty. Plus, and there is a last contribution, which is this one. which is tg minus 1, j, L1 minus j minus 1, L2 to Ln. And you sum over j going from 0 to L1 minus 1. So this is the equivalent of Tutte's equation in this higher genus case where you can have an arbitrary number of boundaries. If it is it clear? Because I will erase the picture now. Okay. But now, the interesting object, which I studied in the case of genus 0 with one boundary, was coming when I was considering generating series for these numbers. And which has this WGN. So maybe I should recall the definition. This is equal to this. You make a sum. You take Tg L1 to Ln, and whenever you've got Li, you multiply by 1 over xi to the power Li plus 1. 1 to n xi to the power Li plus 1. And you sum over L in n to the power n. So I'm just building a generating series for that. Now, what I will do here is exactly as I did before. Yeah? Any question? No? OK. So I will just take this equation for fixed L1, L2 to Ln. I multiply it by what? By 1 over x1 to the power. So I've got L1 plus 1. So it's L1 plus 2 product from j equals 2 to n, 1 over xj to the power lj plus 1. Sorry, L1 plus 1. So I take this equation, I multiply by this monomial in 1 over xi's, and I sum over all possible values of the l's. So that's exactly what I did in the n equal 1 case. Sorry?
Why is that
because just that it's a specific one, so you would expect to have. Yeah, no, it could be, yeah. So a priori, you would have to multiply by product of 1 over xi to the power li plus 1 for I going from 2 to n. And for the first one, it should be 1 over x1 to the power L1 plus 2. But it's just L1 plus 1, so it turns out it's the same. Now, if you do that, and you sum over all possible values of L, what you get is an equation of this type. G prime of x1 WGN of x1 xn, which come from this kind of contribution. This one plus this one, summing over. So your x2 to xn are kind of spectator. But x1, here you will have a x times 1 over x to the power L1 plus 2. And here you will have a sum over I of ti to the power x I minus 1 times what you would like to have, which gives you this v prime of x1 times wgn of x1 xn. But remember that in the sum we're doing here, we're summing over positive L1s. So actually here, when I just make this sum here, I will just get negative powers of x1. While here, if I would just look at that, I would have both negative and positive powers of x1. So I've got to remove the positive powers And this is a polynomial in x1, which I call PGN. So what I will do for the moment is that I underline my x1 just to remember that this is a polynomial in x1, which is a much simpler object compared to the other ones. And now I've got to translate what these other contributions give me. So the first one is a bit tricky to write down. So it's a sum from j equals 2 to n, d over dxj of wgn of x1. Here you look at x, you take the sum, the set 2 to n, and you remove j. So I'm using the same notation as here, saying that when I've got a set as an index, I'm looking at all the xi's where I belong to this index. So here it gives me all the xi's with I in 2 to n, except for xj. What? Yeah, I could include the 1. Just that I'm used to putting 1. So what I did from the beginning of this talk is that I did put the first boundary as a very specific one. So I always want to see it and to put it in front, just to remember that it's marked. I could put it for notation purpose here, but I prefer to keep it there. Yeah, and sorry. So this, we started from wgn. We had n variable. Here we've got n minus 1 variable. And here you've got the x2 up to xn. So you've got here x1 to xn except for j, and here you've got x1 to xn except for x1, divided by x1 minus xj. So that's a good exercise to do that, write the sum, and you will see that this expression can be written under this form. And now we just have the remaining ones, which are much easier to write down. So you write your sum equal to g, sorry. And here it's what? wg1, cardinal of a plus 1, where you've got the variable x1, xi where I belongs to a, wj2 b plus 1, x1, xb plus, and the last term is wg minus 1, where you've got n plus 1 boundary components. x1 appears twice. And here you've got x2 to n. And here it is. I've got all the terms that I had before. So for these two guys, this is very easy to write down. You really have the right factor in front. This gives you really the product of two w's, and this gives you one w here. The only tricky ones are this one, which gives you this d over dx of a difference. Sorry?
X1 appears twice.
Yeah. Look. So here it appeared twice already in the product, because you had this j and L1 minus j minus 1. And here it's exactly the same. So you've got x2 to xn. Here you've got 1 over x1 to the power 1 over x1 to the power j plus 1, 1 over x1 to the power L1 minus j minus 1 plus 1, which gives you 1 over x1 to the power L1 plus 1, which is exactly what I did up there. In some sense, your x1 was associated to the first boundary component, and you look at what happened to your boundary component when you remove this edge. So either you just get a bigger boundary component, but you don't change the number of boundary components, or you cut it into two parts. So some people would call it some kind of cut and paste procedure, because here I did paste my marked boundary component with another one for this one and this one, and I cut it into two parts, or cut and join equation. Okay. Now, the main goal of the lecture today is to solve these equations. So you remember for W01, we had something very similar. We didn't have that, and we had just a product of the W01s here. And the hard thing was to fix this polynomial here. So you could say, OK, here for every g and n, will I have to fix this polynomial by doing all this consideration, defining a new algebraic equation, and so on? And the answer is no. But before going to the very general case for arbitrary g and n, I will have to look at a particular case once again, which is g equals 0, n equals 2. Sorry? Yeah, it is the same. Yeah, I didn't. Yeah, so v prime of x, we put it here. V prime of x is equal to x minus sum over I from 3 to v of ti x to the power I minus 1. So it's exactly the same. And yeah, maybe something I should comment on is the following thing. For the polynomial here, no. Because, yeah, if you think of your v as a derivative, yeah, but it's the derivative of v of x equal I divided by I. Yeah. Just that I don't want to count unmarked faces many times, depending on, it depends whether you put a marking on the edges of your unmarked faces. This gives you a combinatorial factor of I or not. So I choose to do that. OK. Now, I told you this is a polynomial, but how did I get it? Pg n of x1, x2, xn is, by definition, v prime of x1, wgn of x1, xn. So how did I get it? I did write down this, which is what I was expecting to have. And I did remove the positive part and put all the positive part in x1 in wgn. So that's what I will denote by the positive part in x1. So this is a series in 1 over x1. So yeah, this is a series in 1 over x1. I multiply by v prime of x1. It has an expansion both in positive and negative powers of x1, and I just keep the positive part in x1. And it is a polynomial. It includes 0, yeah. That's French positive. And something I want to mention now is that v prime is a polynomial of degree d minus 1. And wgn of x1, xn begins with like it's of order 1 over x1 squared if gn is different from 0, 1. Yeah. I don't know anything about the behavior in the other ones. That's why I'm underlying and saying that I know some information about x1. So it's a polynomial. And I even know its maximal degree. Its maximal degree is d minus 1, the degree of v prime, minus 2. So degree of pgn in x1 is at most d minus 3. OK?
At most and not.
I don't need more. I mean, yeah. I'm interested in solving this equation, so I am just looking for the minimal information I need in order to solve it. I don't want to have a full information about the object I study. Okay. Case G equals 0, n equals 2. So what we want to compute is this one, W02 of x1, x2. So I tell you right now, this will be the last specific case I'm looking at. I'm not doing all the G and M's. And the point is that this always have a very nice representation and a very important role to play. So I just write down this equation for G equals 0 and equals 2. And it gives me what? W02 of x1, x2 is equal to P02 of x1, x2, which is a polynomial in x1, plus in the sum, I just have one term, the other dx2 of W01 of x1 minus W01 of x2 divided by x1 minus x2. That's it. And now what do I have here? I'm using the notation of the previous week. It's m of x1 minus times square root of x1 minus a plus x1 minus a minus. So let me tell you what I did here. Just took this equation for G equals 0 and equals 2. This is not there, because I need G minus 1 to be positive. This is there, this is there. And what do I have here? I don't have much. So I just have that A and B should give me 2. So here I've got W, two possibilities, W02, x1, x2. Just one possibility, yeah. W02, x1, x2 times W01, x1. I've got two possibilities, so I've got a factor 2. So I get what? Wgn times v prime of x1 minus the contribution coming from there, minus 2 times W01 of x1 times W02 of x1, x2. I put it on the other side, and I get v prime of x1 minus 2 times W01 of x1, factor W02 of x1, x2. And if you remember, this is exactly what gives me this expression, which is a polynomial in x1 times the square root. It's okay? So this is just very simple manipulation. Yeah, so that's what I did do last week. It's that you remember that W01 of x1 was a solution to an algebraic equation, and it was giving me that. So this is what we found out last time, right? So I put it there. It gives me that. So it's a factor. So I want to compute W02, G equals 0 and equals 2. I've got a factor v prime of x1. And I've got a minus 2W01 of x1 as a factor, which come from the other side. OK? So I take this on the other side. And it gives me, so I will go backwards if you want, v prime of x1 minus 2 times W01 of x1 times W02 of x1, x2 is equal to P02 of x1, x2 plus d over dx2. Okay, I'm doing things backwards. I wanted to gain some time, but it's the other way around. It's always the case. So if you write down this equation for g equals 0 and equals 2, and you take all the contribution coming from there on the other side, you get this equation. Now I know from the previous lectures that I've got this relation, and it gives me exactly this equation. Okay. Okay, just before the break, a short observation. What do I know there? I know W01, both sides. I know m of x and the square root here. I know a plus and a minus. I don't know this, but I know it's a polynomial in x1. Now, what do I know about, what does it tell me about W02? It tells me already something which is very important. If I want to compute W02, and now I evaluate it at x of z1, x of z2, where this map x is the one from the previous lecture, which is that this defines for me an algebraic equation and two functions x of z and y of z, which are x of z is equal to a plus a minus divided by 2 plus a plus minus a minus divided by 4 z plus 1 over z. Why did I introduce this Riemann surface, this algebraic curve, and this function x and y? It's in order to show that W01 of x of z was a rational function of z. Now here, if I look at W02 as a function of z1, what do I have? P02 is a polynomial in x1. x1 is a rational function of z. X is a rational function of z1. So it's a rational function in z1. This is a rational function of z in z1. That's exactly the way I introduce this change of coordinate. This is a rational function of z1. So I did work quite hard in order to find this map, x of z in the previous lecture, in order to find this W01. But the good thing is that I don't have to compute something similar in this case for z equals 0 and equals 2. What I know from the beginning is that W02 of x of z1 and x of z2 is a rational function of z1. And even more, by definition, W02 is symmetric in its two variables. So it's a rational function in z1 and z2. And this will make my life much easier now, because I will write it as a function of z1 and z2 and compute it from its properties. Yeah, I think we will have a short break now. And we'll restart in 10 minutes, 5 or 10 minutes. OK. So what I was saying just before the break is that actually I'm pretty happy with this expression, even though I don't know what this polynomial is. Because what I know for sure is that W02 of x of z1, x of z2 is a symmetric rational function of z1 and z2. And now I will say more. What I will say is that actually this equation fixes for me which rational function it is. The good thing with rational function is that when you know their poles and their behavior at their poles, you know them completely. And that's what I'm going to do now. And this is some important lemma, which is the following one. If you look at this function of z1 and z2, so you take W02 of x of z1, x of z2, and you multiply by x prime of z1, x prime of z2. The reason why I do that will become clear later today, I guess. It is still a rational function. Obviously, but no. Sorry? No. Yeah, but I will use another notation. So here this is still the same thing. W02 is a function of x of z1 and of x of z2. Yeah, I could call it W tilde, but yeah, but since I will not write it anymore in the following, I don't have to give it a notation. So it's a rational function of z1 and z2 such that it has a unique pole in z1, and it is when c1 goes to z2 to the power minus 1 with the following behavior. Okay. Yeah, there is a minus sign. Behaving as minus 1 over c1 minus z2 to the power minus 1. I square it. And here I've got 1 over c1 to the power 2. Plus part which is regular. And when, yeah? Yeah, when z1 goes to z2 to the power minus 1. Okay. So here I'm telling you that it has, if you look at it as a function of z1, so it's a rational function of z1, and I know that it has only one pole, and this pole is located at z1 equals z2 to the power minus 1, and I've got this behavior, so it doesn't have any residue, it has got a double pole. And when z1 goes to infinity, it behaves as 1 over c1 to the power minus 2. Now, why is that? What I will do is that I will just look at this equation and look at all possible poles that this left-hand side can have in C1 and C2. So, which pole could it have? First thing which might happen would be that here I've got a 1 over x1 minus x2. So a priori, this might have poles when z1 goes to, when x of z1 goes to x of z2. And the first case is this one, the one I want to remove. What happens when z1 goes to z2? X of z1 goes to x of z2, so I've got a simple 0. I've got a 0 here. But above, I've got W01 of x of z1, which goes to W01 of x of z2. So actually, both 0 cancel. So this is something which is regular here. So you've got 0 divided, I mean, you've got something which is a simple pole divided by a simple 0 divided by a simple 0. It gives you something which is regular. So it doesn't have any pole. Now, you can have that x of z1 goes to x of z2 as well when z1 goes to z2 to the power minus 1. Because you had that, remember that x of z is a plus a minus divided by 2 plus a plus minus a minus divided by 4, z plus 1 over z, which is symmetric under the involution z goes to 1 over z. So it takes the same value for z1 or 1 over z1. So this goes to 0 when z1 goes to 1 over z2, but the numerator doesn't, because w01 as a function of z, or w twiddle 01 as a function of z, changes sign when you change z to 1 over z. So this doesn't vanish when z1 goes to 1 over z2. And if you look at the behavior of w01 as a function of z1, you will find out that you exactly have this behavior here. So you just have to take the notes from last week, plug the expression of w01 that we had into this equation, and you will see this behavior. So we are done for poles which might come from x1 minus x2 here. Now, something might happen when x1 goes to infinity. Here I've got a polynomial. So I've got a polynomial grows in x1. And when z1 goes to infinity, x1 grows like z1. X of z1 grows like z1. So I could have a pole here. But remember, p02 as a function of x of z1 is at most d minus 3. Okay? So the degree in x1 is at most d minus 3, and so in z1, since x behaves like z when z goes to infinity, is d minus 3 as well. What do I have downstairs? Now you've got to remember the expression that we've got here. M of x is a polynomial of degree d minus 2. This square root gives you something which is of degree 1. So you've got something downstairs which has degree d minus 1 in x1. So we're done. We've got something which is a polynomial of degree at most d minus 3 divided by something of degree d minus 1. Gives us the right behavior. Sorry? Yeah, but it's, okay. Yeah, if I want to stick to what I said, if I need minimal information, yeah. Just that it was, okay, so simple that I did, okay. But you're right. Okay, so what else could I have? Poles coming from there, pole coming from there here, and actually from W01 for the same thing. Now, the other thing which might happen is that this denominator could be vanishing. So, yeah. Let's look at what can happen. What happens when the square root vanishes? Which means that, z1 goes to plus or minus 1. So remember that a plus or minus was equal to x of plus and minus 1. Now, we could have something which is vanishing downstairs, so a simple 0 at most, which could give us a simple pole. But now, I did multiply by this, x prime of z1 times x prime of z2. Now let's write down x prime of z1 divided by the square root. x of z1 minus a minus. X of z is written here. So we can write it. It's equal to, yeah. But I didn't write down the square root, but if you take your notes from last week, it will be 1 over z. Exactly, 1 over z1. Because you will have, taking the derivative here, you've got this factor times 1 minus 1 over z squared. You take a 1 over z, and you have some z minus 1 over z, which is exactly what was giving rise to the square root here. So actually, even if this looks singular, the point is that x prime is vanishing at this specific point. And this cancels the possible pole going from downstairs. OK, so this is regular there. And now the last tricky part are the zeros of m of x1. OK. And here we will use a kind of argument which is exactly the same one as we did last week for Brown's lemma. Meaning that what one can show is that there cannot be any pole there by showing that order by order in T, the integral of this differential so if you take W02 of x of z1, x of z2, dx of z1, and by the way, now you start seeing why I multiply by x prime of z1. It's in order to have that what I've got there, if I multiply by dz, gives me such a differential. Can multiply by x prime of z2, it doesn't give any contribution. If you integrate it along a contour surrounding the I0 of m of x, this is vanishing. So in particular, since you can have only simple poles here, so we assume that m of x has only simple 0, you can have only simple pole. You're proving that you don't have any residue. So it means that you don't have any pole, actually, at this point. And how do you show that? You just remember that W02 of x1, x2 was a formal Power series in T, whose coefficients are polynomial in x1, which starts with 1 over, polynomial in 1 over x1, which starts with 1 over x1 squared. And this gives you this condition. And because of this condition, you don't have any pole at the zeros of m of x. OK? And then I cannot have any other pole, actually. So it really shows me that I've got this lemma, which is satisfied. Now I'm very happy because it means that I can write down an explicit formula of this W02. So it's a rational function of Z1 and Z2, which is symmetric in the exchange of Z1 and Z2, which has this behavior. So it has a unique pole with this behavior. It has this behavior when Z1 goes to infinity. And there is only one such rational function, which is this one. So I did go through all these computations. So I did derive this combinatorial relation, did write it down in terms of generating series, gave me an equation which looks not that simple. Sorry?
There's actually no property.
What?
No function.
1 square here? No.
Just before.
Yeah.
Division 1 and receive 1 square.
Yeah.
Second factor. Right. Move your finger to right.
Yeah.
Yes. That should be 1
Yeah.
square. Or receive 1 square.
Yeah, yeah. Yeah, C2 square. Yeah, thank you. Yeah. Thank you. Right. OK, so this condition implies this formula for W02, which, as you see, once you know once you know in which coordinate to work on, it's very simple. I mean, that's a very simple formula. Remember that this is a generating series for all genus 0 map with two boundaries, arbitrary lengths of the boundary. And what I like is to write it as x prime of Z1 times x prime of Z2 divided by x of Z1 minus, with a minus sign, minus x of Z2 squared plus 1 over Z1 minus Z2 squared. No, last week we spent quite a lot of time, 4 hours just defining stuff, but in particular finding the W01 of x. And one of the hard parts was to be able to describe this change of coordinate where going from x to z, such that your W01, which was a multivalued function of x, give you a monovalued function of z. This was the hard part. Now for 0,2, actually it goes a bit faster now, because we already have a change of variable going from x to z, and using exactly the same one, we find a very simple formula for W02 of z1 and z2. Now if you want to compute T0, L1, L2, you just have to compute residue of x of z1 to the power L1, x of z2 to the power L2, dx1, dx2 of this guy. So that's pretty simple. Yeah, John? Yeah? So, yeah. Now, first part of the theorem is just an application of this. Second part, the second equality, is just the following observation. This is a rational function of z1, let's say, which has poles indeed when z1 goes to z2 or z1 goes to 1 over z2. Now, if I put this on the other side, indeed, x or x prime, this is equal to the sum of these two terms. That's a pole when z1 goes to 1 over z2, and when z1 is equal to z2. Okay? So indeed. And now if you forget about this part and you say, does it have a pole when z1 goes to z2? This has a pole, this has a pole, but they cancel. Yeah? Minus 1 over z1, z2 minus. Yeah, I think so, yeah. Let me check. No, I think it is, yeah. So you take z1 goes to infinity. Yeah, but you've got the dz1. Sorry? Yeah, yeah. Because you want, so, OK. Maybe I will make a remark about this number. How do we recover these numbers? Yeah, actually, you corrected me when I did this mistake last time. That when you take residue at infinity, you've got a minus sign.
I don't think in terms of residue, I think x is 1 minus.
It's minus 1 over.
How does x
So it's 1 minus 1.
1 minus 1 over?
So dx of z is equal to a plus minus a minus over 4, 1 minus 1 over z squared dz. Is it what you said? Yeah. So what I was saying is that we want to recover these numbers with some positive signs. So let's write it. It's residue when z1 goes to infinity, residue when z2 goes to infinity, of w02 of x of z1, x of z2, x of z1 to the power L1, dx of z1. Yeah, but I was, I did, yeah. Okay. So yeah, we've got 2 minus signs here. Yes. And so of minus 1 over c1, c2 minus 1 squared, and here. Okay, so what's your question? It's about, let's look at L1 equals 1. Yeah?
When z goes to infinity,
Yeah.
it's like minus 1 over z1.
This one, yeah.
Yes.
Yeah. Yeah.
As when you express in terms of x, that makes
Yeah.
1 over x1 squared.
Because I'm pretty sure of the sign.
I can try to look computation and
Yeah, because, I mean, I think I checked it. Yeah, so the question is already here. I mean, do we have this minus or this plus sign? So the question now is what happened? For example, we could look at the simplest case, which should be T0 2. So we should compute it. But yeah, I don't want to do it right now, otherwise I won't have time. Yeah, but there are some misprint in this one. So, but this one agrees, I think. Yeah. So, but this, yeah, because yeah, I did check there are some misprint, but this one I think is right. And yeah, I mean, okay. I did compute some example with this sign, and it was giving positive numbers. But so it was an occasion to remind you that why I did want to compute this generating series is that in order to extract information, which are this number of maps, I compute residues. And you see that, remember that for computing this residue, I was taking W02, x to some power dx. And that's the reason why actually the good function of z is not W02 of z1, z2, but you've got to multiply by x prime, because it comes from the x prime of z1, dz1. The good object you want to study is not a function of z1, actually. It's a differential in z1, because you want to integrate it. And this motivates my definition now for arbitrary Gn. I mean, when I say arbitrary, it's 2g minus 2 plus n. Strictly positive. So, question, do I have to redo all this stuff? Now I will do it a bit faster, and in order to do that, I will introduce the following notation. As I told you, the important object is actually omega, is actually a differential form. And I will call omega gn of z1 to zn the following object. I take wgn of x of z1 x of zn with the same map x as before. And I multiply it by product from I going from 1 to n, dx of z1, dx of zi. So I turn it into a function of the z's and as a differential. Now, up to now, I don't know which property it has as function of the z's. And in addition, for the specific cases I did study before, I make a shift for g equals 0, n equals 2. Sorry? No, dx. So for example, what did I study here? I studied the function times x prime. And this x prime is x prime of the I dzi. Yeah? Yeah. So now, you see, I've got the w here, and I multiply it by the x primes in order to get something which is an I function of z, right? Here I'm doing the same thing. I take the w, I multiply by the x prime, and the only additional thing I do is multiply by dz, as you wish. Okay? So for g equals 0 and equals 2, I will add this. So dx of z1, dx of z2. Sorry? So the general case is this one, and the notation is for g at least equal to 0 and n at least equal to 1. Okay? Sorry? No, there is no stability condition for this. So this is a notation which is valid for arbitrary g and n. And it doesn't mean anything for n equals 0, and I didn't discuss the case n equals 0 yet. So for W02, I just add this part, and for W01, yeah, where did I put it? Yeah, I remove 1/2 of g prime of x of z1, dx of z1, divided by 2. No. What did I want to do that? No, the previous lectures were devoted to computing that. We have shown that omega 01 of z1 could be written under this form, where the function y of z was written last time. And omega 02 of z1, z equals z1, is equal to, I just take what is written there, dz1 dz2 divided by z1 minus z2 squared. So for g equals 0 and equals 2, what I did by adding this term is exactly what I did here. I didn't really like the fact that I had a pole when z1 was going to 1 over z2. So I changed it in order to get something which is a pole when z1 is equal to z2. So these are, maybe a first remark, which is the following. The first function as a function of z explicitly depends on y and x. The second one, omega 0, 2, if you write it as a function of z, it's something which doesn't depend on nor on y nor on x. Actually, if you know the curve sigma, then you don't know where it comes from. You don't know anything about the function x and z, x and y, but you know that sigma is parameterized by z. You can write down omega 0, 2 under this form. And this is a kind of universal form, and that's a general thing, which is that in everything I will do, when I will look at the genus 0 case with two boundaries, it will take a very universal form, which doesn't know anything about any function x and y. It will just require the knowledge of some Riemann surface sigma. What? Yeah. So you've got this. Yeah. Exactly. So no. I mean, it depends. If you look at this equation, it gives you a function y of x. No, this y is y of z. So that's, if you want, I can recall what was going on. Sorry? So you can write it in this way. Yeah, but it's a bad way to write down things, because y of x, you see, it's an equation of degree 2. No, wait, listen to me. It's an equation of degree 2. It has two branches of solution. So if I write it y of x, it's not precise. It has two solutions. Yeah.
But what I'm asking is this y such that if I substitute x and z, y?
It's one of the solutions, yeah. So if you take the right branch of solution to this equation, and you substitute x as a function of z, no, what you can say is the other way around, is to say that sigma can be written as the set of z in the Riemann sphere, such that the set of x of z, y of z in the Riemann sphere, where z belongs to P1. And so there's two functions are such that for all z, the equation E of x of z, y of z is fulfilled. And last week I gave you an explicit expression of y of z. And basically this is the...
What confused me is that previously was the y, one of the y's.
It's not exact. No, it was not exactly the y. It was the y plus v prime.
It was one of the two y's.
Yeah.
W01 is a solution of e of x.
No, it was W01 of x was equal to y of x. So you had 1 over 2 here. Yeah. So you had this kind of relation as function of x. But I agree this is a bad notation. What I want to call y. Yeah, but this is, y is not a function here. It's just, no, y is just a point in the Riemann sphere. Yeah. Up to a shift by v prime of x divided by 2. It depends which equation you have. No. Yeah. Yeah. Yeah, but no, but here I don't. Okay, let's call it P and Q. No, I mean, no, you don't want to have the, you don't want to be confused. So I call it P and Q. It has nothing to do. These are not functions. These are points.
I know. But it's right next to your nose that E of x W01 0.
Yeah. So that's an equation.
That means that it's on that curve.
It means
W0 is one of the possible y's for that.
it's not exactly, because what I call y is you take a solution to this equation. You remove v prime of x divided by 2.
When your y is not y. Y of x is not y.
There is no y here. I mean, I removed it.
Well, there was until you
No, okay, we can.
just say that
No,
it wasn't the same y.
no. So a first thing I can say is the following one. No, but come on. Look, done. A first property here is this one. If you change z to 1 over z, this changes sign. If you change z to 1 over z, W0, 1 doesn't change sign. It's more complicated. You change the sign of the square root only. Yeah, I mean, 1 was the point. It was not written as a function. I mean, if it's your issue, I replace it by P and Q. Yeah?
The other is compositions. There's one x of z for every z. So you could write that as composing it with x of z.
Yeah, but it's ambiguous.
Not if
That's
you compose it.
We can discuss that after. I mean, we can discuss that after. I gave you last week an explicit formula for x of z and y of z. And just keep that in mind. Well, I mean, we can discuss that after. But yeah, I think you were confused about this x and y here, right?
No, because you're using
Yeah, okay.
y plus a constant with the same notations.
Okay. So let's try to go a bit further. And we can discuss notation later. Okay, anyway, if I use these notations, now I can write down the equation I did derive earlier in terms of these omegas. And I will write it in this form. So here I don't do anything. Anything magical. I just translate what I did write down in the last lecture in terms of these omegas. So it reads under this form, Pg n plus 1 x of z0, z of 1 to n, where intentionally here I write it as a polynomial in x of z0 and a function of z1 to zn. Now, remember that I did have to multiply by the x's here. This will be a differential in z1 and zn, but it's a polynomial in x of z0, so I've got to multiply by dx of z0 squared, because I did that on this side. I've got 0 which appears twice, so I had the dx of z0, dx of z0. Plus, and now we've got omega g minus 1 n plus 2 of z0, z0, all the remaining z's, plus a sum over partition of 1 to n into two subsets, g1 plus g2 is equal to g. And here I will put a stable label, and I will tell you what this sum is just after. Omega g1 cardinal of a plus 1 of c0 ca omega g2 b plus 1 c0 cb plus, and now, yeah, I will write it down here. A minus sign, sum over j going from 1 to n. And it's the last long expression for the day. Squared times omega g n of c1 c0 to n minus j minus dx of c0 d over d cj omega gn of c1 to n divided by x of c1 minus x of cj. Okay, I've got this big equation where now I've got this sum of a stable term, what I call stable, which is the following one. This excludes G1 equals 0 and R and A being empty, and G1 is equal to G and A being the full set. Yeah. So I've got this expression. It's exactly the same as I did write down before, except that I translate it in terms of the omegas. And because of the differential form and the shifts, I've got a slightly different formulation. And sorry, here there is a square. And here there is a 0. Yeah. No, so the numerator is, on one side you've got Z0 to Zn, and you remove J. And this one, yeah, there is no Z0. No, because it's d over dZj. No. Yeah, but it's a derivative with respect to Zj.
That's a J.
Yeah. Sorry. Okay. If there is something you cannot read, just tell me. Okay. Yeah. I will do it. So that's the equation we had before. And now the claim is that there is a unique solution which I can write down explicitly, all in one. So first remark is this sum of what I call stable term. What would happen if I would have one of these two terms? J equals 0, A being empty. I would have some omega 0, 1 of Z0 times omega G n plus 1 of Z0, Zn, Z1 to n. Actually, this is present in the equation, but that's on the other side. And what I did is that if I would take the whole sum, I would have this on the right-hand side, but I did put it on the left-hand side because what I want to compute, want to think of it as an equation for omega G n plus 1. Now, let's look at it naively. Say, let's try to compute omega G n plus 1 by induction on the Euler characteristic, minus the Euler characteristic 2G minus 2 plus n. Omega 0, 1, I know it. I did compute it. So I know. This I know it, because it has a simpler topology. This, because of this restriction, I know it, because the Euler characteristic is strictly bigger. Now, what I do, so a priori, actually, this I know, and this I know. Once again, the question is in this polynomial here. Now, what the topological recursion does is that it allows you to remove all these quantity which are not very nice, and this one which you don't know, just by projecting this omega Gn plus 1 in a set of function to which it already belongs, such that this part do not give any contribution. And in order to do that, the first thing we need to do is what we did for G equals 0, n equals 1 and 2, which is that we need to know what kind of function, or what kind of differential in Z0 this quantity is. Which term? This? So, what do you mean as a differential form? So here there is a differential. So it's a one form in Z0, you mean? Yeah. Yeah. So it's all of them are n form, n plus 2 forms. Yeah, but here this, sorry. If you want, I can write it in this way. It depends on the notation I've got here. Because I did write, I should put a twiddle here, if you want. Yeah, okay. Pgn of x0, c1 to n is equal to Pgn, you're right. If I want to be consistent, x0, x of z1, x of cn, product from I equals 1 to n, dx of ci. Okay. And so once again, the first thing I will do is to use this equation in order to know what kind of function of C0, and actually all the other Z's, this omega r, or what kind of differential. What should I start from? So the first thing we can observe is that omega gn of Z1 to Zn. So let's look at it as a differential in C0 and proceed by induction. What I'm claiming is that it's a differential form in C0, meaning that it's the product of a rational function in C0 times dZ0. And we can proceed by induction. It's true for omega 0,1 and omega 0,2. And we assume that it's true for all the terms which correspond to simpler topologies, meaning this one, this one, this one, and this one for the Gn. Everything else are just rational function of Z0, which I multiply by. And there is only one thing which I don't know anything about a priori, except that it's a polynomial in C0 times dx of Z0 squared. So by induction, it's very easy to show that this is actually a rational function. It's a meromorphic differential in Z1 to Zn, which is symmetric. What I mean by that is that omega C1 to Zn, you can write it as omega twiddle Gn of C1 Cn product from I going from 1 to n dzi, where this is a rational function. And once again, when I've got rational function, I've got a lot of information already. And the second statement I want to make now is that I've got some symmetry property, Cn is equal to, and when I change Z1 to 1 over Z1, so if I go from one sheet of my cover to the other one, you remember that I had this picture. I've got the unit circle here with +1 and -1. This is my branch cut. I've got two copies, S minus and S plus. Got a point Z here, 1 over Z there. They correspond to the same value of X. But for omega Gn, if I go from one side to the other side, and I just change one variable, it takes a minus sign. And this is for 2g minus 2 plus n. It is also valid for g equals 0, n equals 1. And when I write it down, you've got to remember that these are rational functions which are symmetric under the exchange of the variable. So this is true for any of the variable I've got inside. So the proof of this lemma is just, again, by induction. We've got this equation, and by induction, we can very easily show that. Once again, the only unknown here is the polynomial, but the polynomial is invariant under the exchange of Z0 goes to 1 over Z0. So it's dx of Z0. So actually, you can see that the right-hand side is completely invariant under this involution. But the left-hand side is something which is skew invariant times what I want to study. And so it gives me that this is skew invariant in order to recover the symmetry. So I think that, yeah. I will stop here. And what we will see tomorrow is how to solve this equation very quickly. It will just take, I hope, let's say 15 minutes, including a lemma. And the idea is what I said. Here I already have some information, but if I look carefully at this equation, once again, I will study the possible poles for omega g n+1 as a differential in z0. It has poles only when z0 goes to plus or minus 1. And then I will just use Cauchy formula in order to get rid of this term and these terms. And it makes the life much easier because the formula will be just an induction on the Euler characteristic, which has a nice feature. And I think that tomorrow after that, I will start to tell you about the general procedure of the topological recursion. I will stop here.